Hello, I'm Wu Peishen. What I want to share today is an article published in JAS in 2024 called Ultraviolet Photodissociation of the N-dimethyl-formamide cation. This study used 180 nanometer as pump laser to excite the molecules into ions. The ions are then dissociated into fragments using probe laser. Finally, the velocity map image and kinetic energy distribution of product are discussed. This is my outline. There will be introduction, experimental, result, and summary. Let's talk about motivation first. This research allows us to gain a deeper understanding of peptide bonds. Peptide bonds are the backbone of proteins and peptides, and their stability directly affects protein structure and function. Fragmentation studies help us better understand how environmental factors such as pH, temperature, or chemical engine influence bond stability. DNF was chosen because it is the simple small molecule containing a peptide bond, allowing us to better understand the electronic effect on peptide-like molecules. Previous studies have focused on the photodissociation of neutral DNF, but there is a lack of research on the photo-induced fragmentation dynamic of the DNF cation. The study aims to investigate the photodissociation dynamic of the DNF ion at 225, 245, 280 nanometer. We also want to understand how the DNF ion fragment when it absorbs UV light and to identify the resulting fragment ions and their energy distribution. They use velocity map image (VMI) to help interpret the experimental result. Next, the experimental setup and principle are introduced. Here, briefly introduce the principle of a velocity map image. Helium at a pressure of about 1 bar was bubbled through liquid N-dimethyl-formamide to generate a mixture of DNF in helium. The gas is spread through a 1.5 mm skimmer and then passes through the repeller plate of a 3-length VNI ion optics. The molecular beam intersects here with both the UV photodissociation laser beam and the VUV detection beam at right angles. The VUV laser beam used to ionize the sample molecules was generated by frequency tripling, the third harmonic of an ND-YAG laser. A polarizer and half-wave plate were used to polarize the VUV light vertically in the image plane, perpendicular to the top axis. Following a short time delay of 50 nanoseconds, the UV photolysis laser beam from a tunable post-frequency double dye laser, pumped by the third harmonic of an ND-YAG laser. Photolysis wavelengths of 225, 245, and 280 nanometer were used in this study. The VNI ion lens consists of a repeller, extractor, and ground electrodes. The repeller plate has a hole in the center to let the molecular beam to the intersection reagent, and the extractor and ground have holes in the center to transmit the expanding Newton sphere scattering distribution to the top tube. By controlling the voltage ratio on the extractor and repeller to achieve velocity mapping condition, the three-dimensional scattering distribution of the fragment traveling through the flight tube is projected onto a two-dimensional ion detector. The ion detector includes a microchannel plate coupled to a phosphor screen. Each incoming ion generates an optical signal on the phosphor, which is captured by a camera. After some calculation, the data was transferred into a kinetic energy released. When a pump laser hits the particles will absorb this light and dissociate into a fragment. The fragments spread in all directions to form a Newton sphere. ion image projects a three-dimensional Newton sphere onto a two-dimensional detector, often called a crushing image. In recent years, slice image methods have been developed. They can direct recording of the three-dimensional distribution, that is, slice image that we used. Next, see the energy diagram on your right hand. The laser energy provides the threshold energy and internal energy of the molecule, and a given energy is not exactly equal to a potential energy, must have the excess one, so which can provide the speed of the fragment. This figure shows the calculated excitation energy of electronic state of the DNF in both neutral and cation equilibrium state, as well as the energy of various dissociation products. Red arrow indicate the photon excitation for ionization and photon dissociation. The red areas represent the energy range accessible based on the degree of vibrational relaxation of ions. On the right, on the appearance energy for each product channel. The ions product by ionization do not immediately reach a stable equilibrium state. They undergo relaxation, where the structure adjusts to a more stable ionic ground state geometry. During this process, some vibrational excitation is generated, that is, internal vibrational energy. Due to the lack of spectroscopy detection data, it is not possible to precisely determine the distribution of various vibrational states of a DNF cation before absorbing ultraviolet photons. Although the initial vibrational state cannot be precisely determined, we can infer the range of final ion energy after absorbing ultraviolet photons based on the photon energy and photon relaxation process. This allows us to estimate the range of electronic state the ion may transition to. DNF is ionized into cation at 180 nanometer and then dissociate using laser of three different wavelengths. We first focus on the primary dissociation channel, including the cleavage of the NCO or N-methyl bond. At all three wavelengths studied, the strongest signal appears at N/Z44, corresponding to the yellow reagent associated with the Nc2H6 ion. This ion is the major product formed directly from the cleavage of the NCO-Mi bond. The table in the upper right corner shows the vertical excitation energy of neutral DNF in its ground state, along with the product formed after cleavage of the NCO or N-methyl bond. From this table, we can see that only the second excited state can produce HCO ions. This explains why the signal at N/Z29 in this green reagent is very weak. We might also expect to observe product from the N-methyl bond cleavage of DNF cation under UV excitation. According to the table, all low energy states except for the third excited state will produce HCO-NCH3 ion. However, at all three photodissociation energy study, we observe almost no signal at N/Z55. From the current discussion, we can summarize two conclusions. First, the amide bond cleavage is selective, producing HCO and Nc2H6 cation as the major product, with HCO cation being produced in very small amount. Second, the primary photodissociation channel involves amide bond cleavage, which far surpasses N-methyl bond cleavage. Below are the velocity map image plot and kinetic energy distribution for two ionic products. Surprisingly, the kinetic energy distribution of the Nc2H6 cation found at the three photodissociation energy are nearly identical. The majority of the excess energy is now released into translational motion of the product, but is instead clearly released into internal excitation of the nascent ions. This part will be explained later. From the relative peak intensity given in table, we see that the intensity of the Nc2H6 ion signal decreases with increasing photon energy, while the signal intensity for the smaller fragment all increased. This implies that these smaller ions are secondary dissociation product of a primary Nc2H6 ion. The Nc2H6 ion formed in the primary dissociation step has a lifetime of at least tens of microseconds and is easy to isomerization. It can further dissociate through multiple pathways to produce these four small molecular ions. When the major fragment ion has sufficient internal energy, second dissociation occurs. These are the velocity map image of the secondary dissociation product. The image of the secondary dissociation product are very similar to each other and to those of the primary product, indicating that very little energy is released into translation during the secondary dissociation step. Additionally, the lack of any angular anisotropy in the image suggests that the molecule undergoes rotational peer-to dissociation. In most cases, the kinetic energy distribution of the secondary dissociation product show only minor change as the photon energy is increased. A special case is the ammonium ion, where we observe a long exponential decay tail in the top signal. This is characteristic of metastable decay, where long-lived parent ions dissociate and form detectable ions outside the interaction energy as they travel through the flight tube to reach the detector. In addition to the simple NCO bond cleavage pathways, NCO bond dissociation can also be accompanied by intramolecular hydrogen transfer. The NCH4 ion can be formed through two different dissociation pathways. One pathway involves the transfer of a hydrogen atom from one of the methyl group to the nitrogen, while the other pathway involves hydrogen transfer from carbon to nitrogen through amide bond dissociation. Since CH2 is less stable than CH3, the latter pathway requires much lower energy. This channel has a lower energy requirement but operates with high efficiency. The NCH4 ion is extremely abundant at all three photodissociation wavelengths. As the laser energy increased, the intensity of NCH4 decreased. This is because the NCH4 ion formed at 225 nanometer has a higher degree of internal excitation, which increases the probability of losing H2 to form NCH4 ion. This is consistent with the conclusion of the others before. In summary, this research presents a study on the UV photodissociation dynamic of the N-dimensional formamide cation, a model system for understanding peptide bond fragmentation. The research used velocity map image and electronic structure calculation to investigate the fragmentation pathway of DNF ion at three wavelengths. They found that UV photolysis leads to selective cleavage of the amide bond, producing HCO and Nc2H6 cation as the major product. Most of the excess energy is released into the internal modes of the fragment. We also confer a minor pathway involves intramolecular hydrogen transfer. The primary Nc2H6 product undergoes secondary fragmentation to form these 4 small molecular ions. Thank you for listening.